Okay, so what do we do? How do we go from our complex general solution to a real solution? So let's think about this problem in general. Let's suppose we have a complex valued function and it solves a linear differential equation. So let's say we have a linear differential equation, like linear operator applied to x equals 0 is some linear differential equation. Homogeneous, that's why I'm putting 0 on the right hand side. And say you have a complex solution. So I'm going to call the complex solution z of t rather than x of t, just because we often use z for complex numbers. So let's call it x of t plus y of t times I. Remember we talked about how complex valued functions, complex solution means we have a complex valued function. Remember how we talked about complex valued functions are just really two functions, the real part function and the imaginary part function. So when we say we have a complex solution, we're talking about two functions, like this, with the property that, so complex solution means when you apply the operator here to z, you get 0. That's what is meant by complex solution. So let's make it second order. And you know what, actually let's make it specifically the kind of differential equation that we are looking at here, just to make it perfectly clear what's going on, and then you can think about how much more general you can make the argument. So let me write this in. Say you have the differential equation ax prime prime plus bx prime plus cx equals 0. And say you have a complex solution, z of t. So then that means L of z is 0, where L is short for a times the operator that takes a second derivative of things that it applies to, plus b times the operator that takes a derivative of the things that it applies to, plus c. So that is what I mean when I say L of z. Okay, so that means the differential equation is L of x equals 0. Okay, so we know this about z, that if you apply this to z, you get 0. So we have a z prime prime of t plus b z prime of t plus c z of t equals 0. That's what that means. Therefore, so now let's work out what is z prime prime, or what is z prime. Let's focus on this one first. If z is x plus iy, then what's z prime? Is x prime plus iy prime. That's what we said in the previous lecture, that this is how you take the derivative of a complex valued function, is you actually just can take the derivative of the real and imaginary parts separately. And what about z prime prime? Well, same deal. You apply another derivative to the complex valued function z prime, and you get this, right? So using those ideas, I can rewrite this here as follows. A, and then instead of z prime prime, I'll write x prime prime plus I y prime prime plus b, and then here I write x prime plus I y prime plus c, and then z is just x plus I y. And I'm just being too lazy to write of t, but really I should say of t everywhere here. Okay, equals 0, right? That was the original equation, equals 0. So let's rearrange it. Let's collect together all the stuff that does not have an I in front of it and all the stuff that does have an I in front of it. So we have ax prime prime plus bx prime plus cx. That's this term, this term, this term. And then for the stuff that does have I in front of it, I have a y prime prime times I. So a y prime prime. And let me pull out the I. plus, and then b y prime times I plus c y times the I here. So there. Now look at what I've got. So these are functions of time, so I'm just being too lazy to write of t here, but it's there. But the idea is that I have this equals 0 for all t, for all time t, right? Because when the original equation was for all t, when we say z of t is a solution, we say we have a solution, we mean that the differential equation holds for all t when you plug in that function of t. So this equation here holds for all t, for all time. Now, when is a complex number 0? So this is something that probably deserved mention when we introduced complex numbers, when we first introduced this idea of complex numbers in the plane, but I forgot to say it. But it should have been said that for a complex number to be 0, a and b have to be 0. And this is part of what justifies viewing the complex plane as a plane, right? The real part axis and the imaginary part axis as two independent directions. So another way to phrase this is that I is a linearly independent object from 1, so that the complex plane really is a two-dimensional plane rather than actually one-dimensional with I. If I were just a funny way of saying 3 or something, then this would definitely not be true, right? You could have like a be -3 and b be 1, and then you would have this be true without a and b being 0. But luckily I is not 3. I is a truly independent thing from any real number. So a complex number can only be 0 when its real and imaginary parts are 0. So this 0 implies, this equals 0 here, therefore we have both ax prime prime plus bx prime plus cx equals 0, and a y prime prime plus by plus prime plus cy equals 0. So in other words, x is a solution to the original differential equation Lx equals 0, and y is a solution to the original differential equation Lx equals 0. So what have we found here? We have found that if you have a differential equation of this form and you have a complex solution, then if you take the real and imaginary parts, so the complex solution will consist of two functions, a real part function and imaginary part function, and if you focus on any one individually as a real valued function, right? This is a real valued function, and the imaginary part also is a real valued function. If you take either of those, they will both be solutions. So this is a way of getting real solutions, is to take your complex solution and take its real or its imaginary part. Those are both ways of getting a real solution to one of these differential equations. So one interesting thing to look at here, now that we're doing this, before I go off of this screen, think about what was needed to get this to work. Basically, what made this work, this idea that the real and imaginary parts of a complex solution, that picking off the x and the y, are themselves solutions. What made this work is being able to take this here and sort of like take the left-hand side applied to x plus iy and then distribute everything and rearrange so that we have stuff applied to just x and stuff applied to just y. So our ability to distribute operations across the sum, the plus here, our ability to distribute across the sum in x plus iy, that is what made this work. So in fact, this whole argument would work for any linear operator on the left-hand side, L, for any linear operator L. So this whole thing doesn't necessarily have to be about this style of differential equation, and does not necessarily have to be second order. It could be any order linear, and this would work. The 0 on the right-hand side was important to get it to work, so you do need homogeneous. One thing that was not important is that the coefficients were constant, so this would have still worked if the a, b, and c were actually functions of time. Then this would still work. Okay, so I hope what you get out of this video is just, if you have a complex solution to a linear homogeneous differential equation, then you can pick off the real and the imaginary parts, and you will have in your hands two nice real solutions to the homogeneous linear differential equation.